Hi, class. Today we're going to be multiplying polynomials, but we'll be dealing with special cases today. Today, I want you guys to walk away with being able to identify and apply the patterns for perfect square trinomials, identify and apply the patterns for difference of squares, and simplify expressions using the special product formulas. Our first vocab word is, what is a perfect square trinomial? Really, it's a result of squaring a binomial. Meaning, if you're looking to the far left, you'll see parentheses a plus b, and that binomial is being squared. What the result of that is actually having the two of the same binomials. So you'll see a plus b squared is equal to a plus b times a plus b. So again, because you have a binomial that is squared, it's really telling you have two of the same binomials. So you could write it out twice like you see, or you can use the formula to the right of that, which is a squared plus 2 times a times b plus b squared, in which case a and b are both any numerical value, or in this case, any variable as well. Or there's a second type of a perfect square trinomial, in which case the difference here is that there's a minus or a negative in between the a and the b. So what you guys see is parentheses a minus b squared. Again, the binomial being squared means that there's two of the same binomials, a minus b times a minus b. But using this formula, you can use a squared minus 2 times a times b plus b squared. And again, it's just a formula that allows us to multiply, or in this case, plug in numbers into the formula rather than having to multiply them like multiplying polynomials. We also have the vocab word, what is the difference, or what is a difference of squares? Really, it's a product of the form of a plus b times a minus b, where again, a and b could be any number or any variable, or a number and a variable, where if you ever come across two binomials that look exactly the same, but the only difference is the sign in between them, in which case you see a positive b and a negative b, you would have a formula that actually gives you a squared minus b squared, where if you're able to identify the a or the b, you guys would be able to just plug in those numbers into a being squared and b being squared. Then we have what's called expanding, and that's what I was referencing earlier with the perfect square trinomial, where if you have a binomial squared, you can do something called expanding, and that's writing the product of the factors as a sum of difference of terms, meaning you're just fully multiplying it out. You're rewriting that binomial as the same binomial twice, a plus b times a plus b. And then finally, we want to be able to have pattern recognition. All this means is being able to identify special product forms to simplify using multiplication without fully having to distribute it. Meaning, what we did last class, which was, again, using the area model, or in this case, using the distributive property, by recognizing it as either a difference of squares or expanding it, we would be able to just simply plug in the values into the formula. So now let's give it a try. So the instructions here are to multiply the polynomials and write the answer in standard form. My first step is to recognize this pattern, in which case they give me x plus 5 squared. I already see that they only give me one binomial, and that it's to the power of 2. And so I can recognize this from my key terms as a perfect square trinomial. Because it's a perfect square trinomial, I can apply the formula. Or you could also choose to just multiply this like we did last lesson. Because I know that it's a binomial squared, I know I could expand this binomial by writing it twice. X plus 5 times x plus 5. In which case, I can use the same methods that we learned last class, using either the area model or even the distributive property. But let's say we wanted to apply the formula. And again, to the right, what you see is our step 2, applying it. On the far right of all of that in red, you see a squared plus 2ab plus b squared, in which case I would be able to use the formula to identify first the a and the b, in which case I can identify my a value as x and my b value as 5. Because I know my a value is x, all I simply do is plug in the x to the a value of my formula. And then same with the 5. I can see that that's my b value. So I would have x squared plus 2 times the b value of 5 times the a value of x plus 5 squared. And now for step 3, all I would need to do is simplify that, in which case I would have x squared, and all I would need to do for x squared is write it out as x squared. For the middle term, I would have 2 times 5 times x would give me 10x. And then finally, I would have 5 squared. And again, squared means multiply by itself that many times. So I would have 5 times 5 gives me 25. So I would have a simplified standard form of x squared plus 10x plus 25. But again, if you're having trouble using the formula, you can still use the area model or use the distributive property to simplify the expression. Now let's try it 4 different times. So on the top left, as you can see, we have also another perfect square trinomial. Actually, all 4 of these are perfect square trinomials with different difficulties. But looking at the top left, I see x minus 7 squared, in which case I can recognize this as a perfect square trinomial. But again, since there's a minus for the 7, I know that this is the second one from the key terms, a minus b squared, in which case I would still need to identify the a and the b so I can plug it into the formula to the right, which is again a squared minus 2ab plus b squared. So I can identify the a as x and the b as 7. And you may say identify it as negative 7. But again, for the formula, you're only identifying just the number or the variable, in which case it's just 7. So I would plug in x for a and 7 for b. So it would look something like this, which I would have x squared minus 2 times 7 times x plus 7 squared. Where for the x squared, x times x is just x squared. Negative 2 times 7 times x is negative 14x. And 7 times 7 is 49. So my simplified standard form would be x squared minus 14x plus 49. Now for the second one. Again, that's similar to the one that we practiced. We have x plus 8 squared. Again, I could expand it and write it twice, or I can use the formula like I did on the first example. And because there is a plus, I would use the formula of a plus b squared, where I need to identify the a and the b value. The a value here is x, the b value is 8, in which case I would plug in x for a and 8 for b, where I would have x squared plus 2 times 8 times x plus 8 squared. And again, just like the last two, x times x is just x squared. 2 times 8 times x is 16x, and 8 times 8 is 64. And so my standard form for the answer for this one would be x squared plus 16x plus 64. And again, you could use the area model or even the distributive property to do so. The third one I have is 2x plus 4 squared. Again, I can recognize this as a perfect square trinomial, where I can see a plus sign in between the two terms. So I would use the formula of a plus b squared, where again, I would need to identify the a and the b value. The a value you may think is just 2 or just x, but the a value is the entire term, 2x. So a would be 2x and b would be 4. So I would go ahead and plug those in. I would have 2x to the second power plus 2 times 4 times 2x plus 4 squared. In which case, my first term being 2x squared, I actually have to square both the number and the variable, in which case I would have 2 times 2, which is 4, and x times x, which is x squared. And then for the middle term, I would have 2 times 4 times 2, which is 16, and I only have one x, so I would bring the x straight down. For the last term, 4 squared, I would have 4 times 4, which is 16. So my final simplified standard form would be 4x squared plus 16x plus 16. For our last one, I have 3x minus 5 squared. Again, I can recognize this as a perfect square trinomial. But again, there's a minus sign in between, so I know the formula would be a minus b squared. Because it's a minus b squared, again, I would have the formula of a squared minus 2ab plus b squared. And just like the last one we did, I need to identify the a and the b, where the a value is the entire first term of 3x. In which case, the b value is not negative 5, it is positive 5. Again, we never take the negative when we're using the formula. In which case, I would have 3x squared minus 2 times 3x times 5 plus 5 squared. Where again, I need to square the entire first term, the number and the variable. Where I would have 3 times 3, which is 9, x times x, x squared. I would have 9x squared. The middle term, I would have negative 2 times 3 times 5, which would give me negative 30x. And then I would have 5 times 5, which is 25 for my last term. But again, with any of these four, I could have used either the area model or the distributive property, and I would have got the same exact answer. Now for a difference of squares. Again, we need to multiply the polynomial and write the answer in standard form. So what I need to do first is recognize the pattern. What I see here is x plus 9 times x minus 9. Again, it's multiplication because there is no sign between the parentheses. And I can already recognize I have two of the same binomials, but they're not the same. One's a positive 9 and one's a negative 9. So I can actually recognize this as a difference of squares. And because it's a difference of squares, I can apply the formula of a squared minus b squared, where what I need to do is identify what the a value is and what the b value is. I can already see that the a value is x and the b value is 9. So I can go ahead and plug in those values there. I would have my a value x, x squared, and my b value 9, 9 squared. In which case, I would have to simplify that. X squared is just x squared, and 9 times 9 is 81. So my simplified difference of squares answer would be x squared minus 81. You could also use, again, just like the last one, the area model or the distributive property to simplify the expression, and you would get the same exact answer, x squared minus 81. Now let's try 4 different examples using the same exact method. Here I have negative 3x plus 2 times 3x plus 2. This one looks different because in this case they look the same, but they're actually not. The 3x and the negative 3x are different. So in this case, you may say, could I use the difference of squares here? You definitely can, but you need to be able to recognize what is the a value and what is the b value. Because you have a negative 3x and a positive 3x, your b value would actually be the 3x. Your a value, because both the 2's are positive, would actually be your a value. So again, my a is 2, my b is 3x. So I can go ahead and plug in this case, my a, 2, and my b, 3x. So I would have my first term, 2 times 2, which is 4. And again, for the second term, I would have to square both the 3 and the x. So 3 times 3 is 9, x times x is x squared. So I would have, in this case, 4 minus 9x squared. But again, I need to write it in standard form. So I would need to put the 9x in the front. So I would have negative 9x squared plus 4, which is standard form. And the second one looks a lot more like the first one we did. But in this case, I have x plus 4 times x minus 4. And again, anytime there's no sign in between the parentheses, what you have to do is multiply. And I can already recognize this as a difference of squares. In which case, I could use the formula of a squared minus b squared, where I can identify the a as x and the b as 4. And I can know that the b is the 4 because I have a positive 4 and a negative 4 here. So all I need to do is plug in those two values, in which case I would have x times x, which is x squared, and 4 times 4, which is 16. So I should have x squared minus 16. That would be my standard form of my answer. For the second one, the third one. I have 5x minus 7 and 5x plus 7. I can already recognize that they're both very similar binomials. The main difference is that the 7 is negative and the 7 is positive. In which case, I know that this is a difference of squares again. So I can simply use the formula of a squared minus b squared, where I can recognize that the a is 5x and the b would be 7. So I would plug that in. 5x squared minus 7 squared. And for my first term, again, because it's a number and a variable, I need to square both the number and the variable. So 5 times 5 is 25. X times x is x squared. Then I would square 7. 7 times 7 is 49. So I would have 25x squared minus 49. That would be my final answer for number 3. And then finally, number 4. I have 2x minus 10 times 2x plus 10. In which case, I can recognize this as a difference of squares because I have a negative 10 and a positive 10. And the leading term would be 2x and 2x, so I know that both have the same exact value. So I would be using the same exact formula of a squared minus b squared, in which case I would have to identify the a and the b. The a being the 2x and the b being the 10. So I could go ahead and plug it into my formula. 2x squared minus 10 squared. So again, for my first term, because it's a number and a variable, I need to distribute the exponent to both. It would be 2 squared, which is 4, and x squared, which is x squared. So I would have 4x squared minus 10 times 10, 100. So my answer would be 4x squared minus 100. But again, with any of these 4, you can use the distributive property or the area model, and you would get the same exact answer on all 4 of these questions. Now what I would like you guys to do is go to Canvas and click on today's mid-lesson assessment, Multiplying Polynomials Special Cases. Answer the questions using your notes, and again, you will get points based off correctness, so make sure you try your best and use your notes. Today I'm not here, so I can't pull you to the side and check and see if you did it correctly. But what I recommend is going to Delta Math today and finishing the Delta Math in class, because you definitely have enough time to do the mid-lesson assessment and the Delta Math and finish both within class. Again, both will be due on your next class, or on Thursday, on Wednesday. So again, make sure you finish your work before coming to Thursday's class, because on Thursday we'll already be going into reviews. I hope you guys had a great day, and I'll see you next class.